Good morning or good afternoon, depending on where you are joining from. Thank you so much for being here today. My name is Matt Morrison from the University of Winnipeg's Department of Geography, and I am one of the co-conveners of this session on ecosystem carbon cycling, along with Miranda Hunter and Megan Schmidt of the University of Waterloo. We look forward to hearing about all of the innovative methods and exciting results that you have offered to present. I myself in Winnipeg am joining you from ancestral lands on Treaty 1 territory. These lands are the heartland of the Métis people. I want to acknowledge that our water is sourced from Shoal Lake 40 First Nation. I understand we are all joining from a variety of locations and encourage us all to commit to begin or continue to learn about the pre-colonial history of this land. Some brief housekeeping before we begin today. For this meeting, closed captioning is available. I believe by default, closed captioning is turned on. You should have the option to toggle it on or off, except for mobile devices with the live transcript button. For your questions today, following the speaker's presentations, please either type the question into the Q&A box and we can read it aloud to the speaker, or put a request in there to speak and we will be able to unmute you so you can ask your question aloud, or if you'd like to discuss directly with the presenters. After the session, we will run a short promotional video for next year's annual CGU meeting held in Saskatoon with the theme of Science Serving Society. This will be the first in-person meeting run since 2019. Looking forward to attend, and we hope to see you there. Just briefly for an overview of today's presentations, we have the first 4 presenters at 20 minutes each, and our 5th speaker will be a 10-minute presentation, and those time slots are inclusive of time for questions. I believe that is all the details and housekeeping for today. So even if we have a few extra minutes of leeway for the speakers, we can get directly into it. Our first speaker is Tracy Rankin from McGill University to discuss partitioning of autotrophic and heterotrophic respiration in an ambotrophic bog.
Hello, everybody. I'm just gonna share my presentation. There we go. So thank you. Oh, hello. Sorry, I had to start my video. Okay. So I'm from University of McGill, as Matt said, and I'm talking to you about partitioning autotrophic and heterotrophic respiration. So before I get started, of course, I want to thank everybody who's helped in all of my field work, all of my supervisors and committee members, of course, and of course, all my funding sources and such before I get started. So we all know that natural peatlands sequester a large amount of carbon in the soil, and that the sink and source strength can vary depending on different weather conditions of the different years and such. And so this variability seems to be due to changes in ecosystem respiration and gross primary productivity, and different studies vary in eddy covariance techniques or using modeling techniques can pretty much accurately predict those components of the carbon cycle. But what we've seen is that respiration is a little bit more complex than we once thought, especially when it comes to partitioning ecosystem respiration into its autotrophic and heterotrophic components. So autotrophic respiration, which should be respiration by plant parts, whereas heterotrophic respiration is from the microbial bacteria in the soil. There's not really a standardized or universal definition of what AR and HR are, especially when it comes to where root dynamics would play a part. So roots can technically be part of the plant and so be part of autotrophic respiration, but they tend to also assimilate carbon rather than take it in through photosynthesis, which would mean they act more like a heterotroph. And so this kind of gives a slight complexity to the way we try to partition these things. And And so the factors that drive these two contributions, I'm going to refer to them as AR and HR just for simplicity's sake from now on, is AR tends to be driven by environmental variables as well as vegetation dynamics, whereas HR tends to be more through microbial biomass or nutrient availability, decomposition rates, and such. But what we've been seeing more and more is that HR tends to have a more dynamic nature to it than we once thought. And in sedge-dominated ecosystems like fens, for example, you actually see this, the roots of the plants essentially priming the microbial activity below. And so it's more sort of dynamic than we once thought, in that we have what we call, or what we're naming, plant-mediated heterotrophic respiration, whereby the rate of the litter supply is actually related to plant production through root-soil interactions rather than just plant biomass like what we once thought. And so there's a need to do these direct methods of partitioning AR and HR to better understand the spatial and temporal dynamics of these components, as well as the need to couple above ground production with the below ground processes. And so because we've been seeing this in sedge-dominated ecosystems, but not, or it hasn't at least been documented very well in shrub-dominated ecosystems like a bog, our main objective then is to determine the contributions and dynamics of AR and HR at Melbourne, an autotrophic bog in Ontario. More specifically, we want to determine those contributions on the temporal spatial variability and the contributions of AR and HR using autochambers, and then compare those contributions to a fen, the Daguerreau fen more specifically, in Umeå, Sweden. And then, of course, we want to, using the auto chamber measurements, try to see if they support the manual chamber measurements that were taken at the site as well, and try to tease out any benefits or disadvantages of using different methodological approaches of trying to partition these components. And so our main three hypotheses are that, first, that the manual chamber setup will follow the trends and magnitudes in respiration of the darkened auto chambers more closely than the ER that you derive mainly from nighttime relationships with temperature. The second hypothesis, is that the shrubs would have a more intimate symbiotic relationship with the mosses than do the sedges. And we think this because we believe it's the mosses that are acting as the heterotrophic component to respiration, whereby they use a mutually beneficial symbiotic relationship with the shrubs. So the shrub roots provide the carbon to the mosses to be refixed, and then the mosses in turn provide the water and nutrients available to the shrubs. And we don't see this as much in the sedges. The sedges tend to just sort of prime the microbial bacteria in the soil below. And the third hypothesis is that we think the AR to HR ratio will be higher in shrub-dominated peatlands than in sedge-dominated peatlands. So to do all of this, we used 5 automatic chambers at Melbourne, and we had 1 full year of baseline flux measurements of CO2 in 2017. And so we didn't do anything to the plants all of 2017. We just sorted to see if the shrubs are acting in the way that we want them to, or in that we expected them to, and they did. And then in 2018 and 2019, we did manipulations to the plots. Unfortunately, our data from 2018 was lost due to some leakage in the tubes of the auto chambers. So what you're going to see in the results section is just the results from 2019's manipulations. So what we did was we had 2 clusters of auto chambers. Auto chambers 1, 2, 4 is one cluster that all acted similarly in 2017, and auto chambers 5 and 6, which acted similarly. The 2 clusters, though, didn't act as similarly as you would expect, and we'll sort of delve into why we think that might be the case in a little bit. So in each part, we had 1 plot that was act as a reference, so we didn't do anything to the plot, and in the other plot, we darkened the chamber, so we put aluminum foil to block out all the sunlight, and then we removed all the above ground vegetation. So in these cases, we assume that the vegetation removed plots act as our heterotrophic respiration. So we have to assume, though, that the residual sort of roots are decomposed completely, which may not always be the case, but it is the assumption we had to make for this this methodology to work. And it was a pretty accurate assumption, to be honest, because there wasn't really very much reclipping that needed to be done throughout the years. So I'd say it's a pretty accurate assumption, but we have to state that as a limitation to the study. And then in the cluster of auto chambers 1, 2, 4, we also just had a plot where we darkened it, but the vegetation still remained. And we did this just to get at the sort of methodological approach, which you'll see in a second. And then finally, AR, the autotrophic component to respiration, was derived from ER minus HR. So ER and HR are measured directly through the plots, and then AR was derived as the difference between the two. And then we compared that with some of the manual measurements that we had from the plots as well. So the first set of results that I'm going to show is on the bottom left here. We show the ER that was measured at using the nighttime relationships with temperature versus the darkened plots in that 1, 2, 4 auto chamber cluster. And that's here at the bottom left. And on the top left is the CO2 fluxes from the manual chamber, so also ER and HR too. And then I put in the graph, I guess you can call it, of environmental variables just to show sort of the trajectory of the weather conditions at the time. And so when I go back to sort of the methodological approach hypothesis that we had, we found that ER measurements from the darkened plots, that's the ones during the day, darkened during the day, follow the magnitude and trends as seen in the manual chambers, and the ER derived by the nighttime relationship with temperature as overestimated. And this seems to be the case mainly when it was wetter and cooler. So temperatures hadn't started to sort of get to its max yet, and water tables tended to drop, but we're still within the 30 to 40 centimeter range, which would influence what happens with the plants and such. And then it's only when it became really, really dry, when water tables dropped below 45 to even 50 centimeters below that, that's when the ER tend to be less overestimated, and where actually the darkened plots were a little bit higher than what we had seen in the manual chambers. So ER measurements tend to be influenced by methodological approaches. That's what this seems to suggest. And we think it has to do with photorespiration effect. So photorespiration, which is sort of the photosynthesis, but backwards in that it takes in oxygen rather than CO2, kind of the reverse process. And that tends to be reduced when you're taking dark respiration measurements during the day. But the environmental variables we see make a big factor on what happens with this photorespiration. So photorespiration has been shown to be stimulated in high temperature and water stress conditions. So when it became drier throughout the year, or throughout the growing season, the ER then was not as overestimated, and the ER derived by the nighttime relationship with temperature is actually closer to what we found in the manual chamber plots. And because you have more of this photorespiration during the day, then the darkened plots are what had sort of the higher values in here. So we thought that was pretty cool to show in the first case. The second thing we wanted to show was what happens with HR, and try to sort of delve into the more dynamic nature of heterotrophic respiration. So on the right, we have ER and HR from the auto chamber 1, 2, 4 cluster, and the ER-HR from the chambers 5 and 6 cluster. And what we see is that the chambers 1, 2, 4 cluster in both ER and HR have magnitudes that are very similar to what we found in the manual chamber plots. But in the other cluster, the chamber 5-6 cluster, it's actually much lower in both ER and HR. And we think this has to do with the fact that there was a difference in vascular plant cover. So Miranda Hunter, who is part of this panel also, or one of the conveners of this panel, did some of the biomass measurements for us in 2019 at the site. So thank you very much for providing us with that. And she showed that in this cluster of chambers 5 and 6, it's actually a lot less shrubs cover in these plots than in this cluster of plots. And so we think that because sphagnum or mosses are more sensitive to changes in different CO2 concentrations, we think that the vascular plant cover can influence both the ER, but also the magnitude of HR, whereby when you have less shrubs to provide that carbon to the mosses to be refixed, then you have the less HR. You wouldn't expect there to be less HR because heterotrophic respiration is just supposed to be from the peat itself. So one would expect that the HR from this cluster and this cluster would have been the same. But because it's not, we definitely think that there's a sort of plant influence on HR, not just on regular respiration in general. The trends, though, of the ones where of this cluster here actually follow the trend in the HR that we find in the manual plots. And we think this has to do more with the environmental variables. So there was some sporadic rain events that happened right in this section here, right where it dips down a little bit. And it's in this cluster that you see, similarly to what was found in the manual plots, that the water table rebounded just a little bit. Whereas in this cluster, they didn't. And they actually just continued to get a little bit more drier. So these ones were slightly more drier in or higher water table depths than this cluster was. And we think that played into the fact of there being a difference in the trend in HR. So water table depth or soil moisture of some sort tends to sort of influence HR as well, but we do think it's a much more dominant process of what happens with the plants that is a greater factor in there than what we would have expected in general. So we thought that was cool. And then the final thing that we looked at was what happens with the AR contributions. So on the top left, I have AR percentage of in the manual chamber plots, and then the AR percentage from that cluster of 1, 2, 4, and the AR percentage of the cluster of chambers 5 and 6. And so what we saw was AR is actually pretty high at the bog, which is pretty what you would have expected. It's between 70 and 80-ish for the majority of the time, until it got really dry. And when it gets really dry, the AR tends to drop. And that's what we saw in the manual chambers and in this cluster, but not as much in this cluster. And we think that also has to do with the fact that there's a vegetation difference, but that's more what we expect because autotrophic respiration definitely is influenced by the plants. And so because this cluster tended to have a little bit more of this other type of shrub species, we think that may be playing a factor. It may also be, though, that there's a difference in potentially the residual decomposition of the roots below in the clip plots that may be driving this as well. So I'm not sure if we can tease that out per se in general, but we do think that it is a difference in species coverage that also may affect AR. So the magnitude of AR definitely is affected by the environmental variables just in general, but the difference between sort of the local effects tends to be more vegetation dynamic driven. And when we tried to compare that with a different site, so the fen in Sweden, for example, we found that the AR to HR ratio at the bog was about on average about 3.0. And this was both in the auto chamber. So this is the auto chamber AR to HR ratio. But when I do it for the manual chambers, I also found an average of around 3 as well. And we think that it's because there's a higher above ground biomass of the shrubs than in the sedges, which tend to have a lot more below ground biomass associated with them. So their roots, the sedge roots, tend to expand more vertically down, whereas the shrubs tend to spread out laterally within the first like 20 centimeters and allocate a lot of their energy to the above ground stems as well. And so when we compare this ratio with the fen seem to have a much lower ratio of around 1.2. Now their temperature was much lower. They're much more north than we are, so their temperature's a lot lower, and their water table, because it's a fen, is a lot greater. It's closer to the surface than what we have here, so it's a lot more wet. So definitely there could be an environmental variable aspect in here too, but in the manual chamber setup that I had, we did do measurements on the sedge species that were at the site, at Melder, at the bog, and we saw that their AR to HR ratio was actually closer to what you would find at the fen. So we really do think it has something to do with a biomass difference here, or again, with vegetation dynamics being a lot more a factor than we once had thought that it played a role. And so to conclude everything together, I'm going to go back to my hypotheses that I said at the beginning. And the first was that the manual chamber setup will follow the trends and magnitudes and respiration of the darkened chambers more closely than those derived from the nighttime relationships with temperature. And we only found that when it was wetter and cooler towards the beginning of the growing season. So our answer to that one was sometimes. In the second one, we had that the shrubs have a more intimate symbiotic relationship with the mosses than do the sedges. Now, we said maybe because there's definitely a component or a factor of environmental variables that play a role in here. But the fact that the magnitude of HR differs with vascular plant cover, whereas the trends maybe are more influenced by the environmental variables, that kind of suggests to us that definitely plants have a much more important role than we once thought. And finally, the AR to HR ratio will be higher in shrub-dominated peatlands than in the sedge-dominated peatlands, and that is in fact what we found, that the shrubs have a higher above-ground biomass, and so AR, despite having a greater potentially HR as well through the mosses, AR is much higher, and so we think that is the reason why we have a higher AR to HR ratio. And that is it for me. Thank you.
Excellent. Thanks so much, Tracy, for the excellent talk and that really interesting comparison of results, especially across continental. So if there's any questions, please throw them in the Q&A and can either unmute or read them aloud. Not seeing any quite yet. I had a quick question, Tracy. It was interesting thinking of the importance of shrubs in the context of the sort of shrubification of the north that is being much discussed. And I'm not sure if these particular species are the ones that are encroaching northward, but do you expect to see a sort of space for time substitution where the current partitioning of AR and HR southerly might become more typical of northern more peatlands as these species become more dominant?
That's a good question. Possibly, yes, but I mean, it really depends on the mechanisms of the plants themselves. So the way that the plants sort of metabolize carbon and its relationship with the various environmental variables with climate change and such will affect how much of those can actually spread or not spread. So what we found was sedges are a lot more competitive species than, or plant type, we call it plant type, than the shrubs are. So you might actually see more sedges than you would shrubs potentially. But if the conditions arise that allow for more of the shrubs there, or if you can maintain that symbiotic relationship with the mosses and the shrubs together, or have the conditions that allow for this sort of mutual beneficial relationship to occur, then yeah, then it will definitely have more shrubs than you would other types of peatland plants, I think.
Awesome, thanks. Yeah, definitely something to keenly monitor. And I know some of the earlier hydrology sessions had a few northern Morris speakers who were looking at this with remote sensing and field observations as well. Pending any other questions to arrive shortly in the chat, then we may be at the right time to move on to our next speaker. So again, with a 20-minute slot, including time for questions, is Nataša Popović from the University of Waterloo, who is speaking on the fact that plants matter, which I agree, quantifying the role of vascular vegetation on the carbon dynamics of a constructed upland fen complex. Thanks.
You guys see my screen and everything okay? Yeah?
Yeah, it looks great.
All right, perfect. All right, so hello everyone. Let me just move this, sorry, toolbar out of the way from Zoom. Okay. Hi everyone, and Thanks for that introduction, Matt. Again, my name is Nataša Popović. I'm a PhD candidate at the University of Waterloo in Ontario, Canada. And today I'll be speaking about the carbon dynamics of a constructed upland fen complex following the development of vegetation. Before getting started, I'd really like to acknowledge and thank all of our partners and especially the team at the University of Waterloo that makes working on this project possible and the long, exciting field work possible. And it spans three labs at the University of Waterloo. And I really just want to say thank you and really appreciate all the co-authors and all the help with this project. So to get started, resource extraction in the Athabasca oil sands region includes widespread surface mining, resulting in the disturbance of the natural landscape. And this pre-disturbance landscape in northern Alberta is comprised of a mosaic of upland peatland complexes that are dominated by fens. And so as we know, these environments provide really key ecosystem services such as water storage, carbon sequestration, and biodiversity. As such, these landscapes have really become the focus of recent mandatory reclamation efforts in the region. And it's really important here to note that reclamation differs from restoration in that there is none of that original landscape remaining, and we're required to build the system from scratch. And this includes laying down the substrates and reestablishing hydrologic connectivity. As reclamation efforts in the region typically use post-mine waste materials, things like tailing sand or petroleum coke, as substrates during construction, the overall trajectory and end result of these reclaimed systems, particularly in terms of plant function and succession, is largely unknown, as the structural and hydrogeochemical characteristics of these construction materials are vastly different than those found in natural settings. And so as a result, these reclaimed systems will likely lead to the development of hybrid or novel landscapes that may be slightly physically different, but functionally similar to these natural pre-disturbance landscapes. And so the overall goal of these systems is to be functionally similar. However, functionality can really be defined in a number of ways. And so here we've provided a few benchmarks that we hope this constructed system can reach. The first being be capable of supporting a representative assemblage of species, for it to be carbon accumulating and really resilient to normal periodic stresses. As we all know, vegetation plays a really crucial role in surface atmosphere exchanges and overall ecosystem performance. And so we need a better understanding of how specific plant communities use carbon and water resources and whether they can persist and function at all in these novel ecosystems. And so here I'll provide an overview of plant development in this constructed site and also quantify some of those carbon fluxes at 5 years post-construction. To begin, I'll just quickly introduce the constructed site itself. The Nicanoti Fen watershed is a 32-hectare watershed that's comprised of 4 surrounding slopes, an upland and a fen peatland. Here in this study, I really only focus on the upland and fen landscapes of the system. And the system itself was designed based on numerical modeling of ideal geometries and substrates for successful ecosystem function within the region's subhumid climate. And this here is actually really quite important, as in the Western boreal plains of northern Alberta, evapotranspiration rates frequently exceed precipitation inputs, and this results in periods of water stress. And so from a functionality standpoint, it's rather important that the vegetation we plant in these systems is able to withstand that periodic hydrologic stress and continue sequestering carbon. And of course, we don't just want things to die off in 5 or 8 or 10 years. Here, the fen itself consists of a 2-meter thick layer of donor salvage peat, and it has a near surface water table and relatively wet edaphic conditions. And it was planted with a mix of both fresh and salt tolerant species, as we expect the system to be salty due to the substrates used. And here it's dominated by sedges, mainly carex, but there is some juncus and typha as well. The treed upland is a much drier landscape, and it consists of about 3 meters of tailing sand aquifer overlain by a salvage forest floor materials. It is a mixed treed upland and consists of both coniferous and deciduous species and has a kind of grassy brush understory. And so in order to capture the plant development and also examine the carbon dynamics of the system, Here we've used a real wide range of techniques, including ecosystem scale techniques through remote sensing and eddy covariance measurements to capture really that temporal plant development and overall carbon performance of the system, and then paired it with plot-based chamber measurements in order to really understand how specific plant communities are functioning under varying environmental conditions. And so in today's talk, I'm really going to largely focus on the results of this plot-based measurements. And so here we used, again, the chamber method to measure CO2 fluxes from 2017 to 2019. And this is really years 5, 6, and 7 post-construction. And it's important to note that during this time, the vegetation is already well established. And so really the methods consisted of weekly measurements of a number of plots in both landscapes, capturing the different dominant plant species. In the fen, that's the Carex, Juncus, and Typha. In the upland, that's spruce, jack pine, aspen, and balsam poplar, and as well as the understory. Really interestingly, in the upland, due to the juvenile nature of the tree stands and average tree height really only being between 140 and 180 centimeters, I was lucky enough to be able to actually fit whole trees into the chambers themselves by stacking multiple chambers together and measure specific fluxes for whole trees, which was really interesting. And for anyone who's ever used the chamber method, I can really say it's just incredible to see how much carbon a tree can sequester in 3 minutes. And so these are the methods I will really be focusing on for most of the results discussed in today's talk. To quickly give an overview of how plants have developed at Nikonoti, here I used a Landsat 8 multispectral imagery and calculated an enhanced vegetative index. And here you can really clearly see how the vegetation has developed over time. Here an EVI signal greater than 0.2 represents vegetation or anything colored in green in that second row of figures. That row of figures shows the mean EVI values for the month of July, which is representative of peak season here. And so we see that the sedge-dominated vegetation in the fen, which is this upper area here, really becomes well established and widespread by 2015. And this is only 3 years following construction. And then any variability that we see from 2015 onwards is really attributed to any environmental factors such as wetter or drier seasons or changes in water quality. In the upland, we see that the upland develops at a bit of a slower rate, and this is due to treed species taking a little bit longer to mature. But we do see that from 2017 onwards, the vegetation in the upland becomes robust as well. And so diving into the actual carbon dynamics of the system, we see that the fen shows a marked increase in plant productivity, or GPP, here shown in green, between 2013 and 2014, and really coincides again with that growth of the vegetation. That plant productivity remains relatively stable once the vegetation becomes well established. And again, any fluctuations seen here are likely due to environmental factors. We can also see that the fen very quickly begins to uptake carbon, with net ecosystem productivity being quite stable from 2015 onwards, and the system being a carbon sink from 2015 onwards. As a result of the vegetation becoming rather robust and widespread rather quickly, the wet edaphic conditions and the lack of bare ground overall, we see that respiration rates in the fen are also rather low from 2015 onwards. And again, this is due to those wet adaptive conditions and full vegetation coverage. In the upland, we see that the carbon dynamics show a similar marked increase in GPP, or plant productivity, once that vegetation becomes robust in 2017. However, due to the rather dry adaptive conditions and thin litter layer, respiration rates remain relatively high in the upland. However, we do see with that increased CO2 uptake and plant productivity that the system is approaching a carbon sink trajectory. And it's expected to reach this in the near future as that canopy continues to mature. And so for the remainder of the talk, I'll really just be focusing on the 2017, 2018, 2019 field seasons. just a little bit of buffering. Okay, here we go. So taking a look at the overall edaphic and meteorological conditions, as the two landscapes are adjacent to one another, they've really experienced similar meteorological conditions in terms of temperature and precipitation. However, during this study period, we did luckily get to experience both a dry year in 2017 and 2 wetter years in 2018 and 2019. Moreover, it's really important to note that the timing and frequency of rain events in 2018 and 2019 were rather different. In 2018, it was punctuated by really these large, intense rain events. Notably, we got about 90 millimeters of rain over the course of about 3 days. And this subsequently resulted in a lot of flooding and waterlogged conditions persistently in the fen, versus in 2019, where there was more of these smaller weekly or daily events occurring and just more overall wetter conditions during the year. In terms of edaphic conditions, we see that the two landscapes are rather different, again, due to these differences in substrates. One is a peat substrate and the other is a mineral soil. And of course, differences in water table position as well. We do see more of a range in fen soil moisture in 2017 during that drier year due to the prolonged dry conditions resulting in some water table drawdown. And so we do start to see a little bit of change in that soil moisture. We see almost the opposite in the upland, where persistently wetter conditions in 2019 and steady rainfall result in a little more range in that upland soil moisture. And of course, due to these differences in substrates and in overall soil moisture, we do see differences in soil temperature as well between the two landscapes, with the soil temperature in the fen being slightly lower than in the upland. When we take a closer look at the spatial distribution of water table position and also salt distribution, we see that overall 2017 had the overall lowest water table positions, and 2018 really shows a lot of regions with that ponded water and above ground water table, where everything, the whole region is basically ponded. However, we do see in all 3 years that there's a lot of spatial variability in terms of water table position, and this really dictates where certain plant communities become robust and persist. For example, the taifa tends to persist in the ponded, rather wet areas. Carex occurs kind of throughout the site, but prefers wetter areas, and the juncus appears to favor the drier conditions. We also saw changes in water quality. In 2018, we saw a rather large influx of sodium. And again, this is due to some of those substrates that are used that are byproducts of the bitumen extraction process. It's important to note here that in all years, 2017, 2018, 2019, the entire system is inherently salty. In 2018, it was just an even saltier. And this is likely due to high evapotranspiration rates in 2017 and in 2018 that kind of resulted in pulling up some of that mobile sodium to the surface. And so when we take a look at the spatial CO2 fluxes here, this is net ecosystem exchange for the both landscapes. We see that these environmental conditions, such as changes in water table depth and salt, impact carbon uptake in both systems. We clearly see the slightly lower rates of carbon uptake in 2017 compared to wetter years in 2018 and 2019. However, it's important to note that while these rates are slightly lower than in wetter years, they're still well within the range of what is measured at natural sites. We also see the effects of, in wetter years, still water table position and also salinity, where we see that wetter areas tend to have slightly higher fluxes and a little more carbon uptake occurring, and that the pockets of saltier regions tend to have slightly lower carbon fluxes. In the upland, we also see the importance of system design and abiotic conditions on overall plant emergence and persistence. In the northwest corner, which is this area here, this is the region that has the thinnest capping layer and also the lowest soil moisture rates for the upland. And it really results in stunted growth of vegetation and more sparse understory and just overall decreased plant health. And we see that is kind of mirrored in the net ecosystem exchange and carbon uptake of the upland versus that northwest corner in the bottom there, where the vegetation is thriving and well and healthy, and the carbon fluxes remain high. Next, we take a look at more species-specific trends as we see that in the fen, all of the species and all of the plant types are really sequestering carbon at rates similar to each other, with the exception of Juncus maybe performing a little bit better overall. In the upland, we see clear trends between tree types, with coniferous species sequestering slightly less carbon dioxide than the broadleaf species. And we see that the understory really is performing as a carbon source overall. When we take a look at the carbon flux components of GPP and ecosystem respiration, here we can clearly see the seasonal trends, with both GPP and respiration being lower in May during the earlier growing season, as plants have not yet greened up. And lingering winter conditions might result in suppressing some of those respiration rates. However, things quickly pick up in June and July. And once that vegetation greens up, we really see some interannual trends, especially based on those environmental conditions. Here we see that Juncus performs better, particularly in dry years. When we look at 2017, it has a higher overall plant productivity, but it also has a higher overall respiration, and this is likely due to the dryness of the plots where this Juncus is dominated. Overall, we see that type of plots exhibit the overall lowest rates of photosynthesis, and also due to the persistence in wet ponded areas, the lowest respiration rates. But however, it's important to note that we see that overall plant productivity continued during increased salinity rates in 2018, and at rates comparable to both 2017 and 2019. Overall, 2019 again was kind of the wettest year and had a lot of overcast days, and so overall photosynthesis rates are slightly lower in 2019 in all of the species, and the overall respiration rates are slightly lower as well. When we look at the upland, we see clear trends linked to the phenology of tree types. Here we see the coniferous species plant productivity remains relatively stable throughout the growing season in May and in July and in August, compared to broadleaf species where there's a clear increase in plant productivity in July when leaf area is largest. And again, those broadleaf species experience kind of that foliation in May, peak season in kind of July, August, and then slowly taper off and start to senesce. We also see that the tree vegetation has a much higher plant productivity rate than the understory, which was expected. And we do see that respiration rates remain relatively stable throughout the entire upland across species in terms, and this is largely due to, again, those dry edaphic conditions. But we do see that aspen has larger rates of respiration, and this is likely due to the fast growth and expansion of the species, as well as their near surface rooting system increasing some of those respiration rates. Overall, when we take a look at the plot scale carbon fluxes as a whole from each landscape, we see that the fen fluxes remained relatively similar despite large changes in both water inputs and salinity. As expected, the tree vegetation is sequestering more carbon than that of the vegetation in the fen. However, due to those dry edaphic conditions and lack of a litter layer, in the upland, we do see higher respiration rates. And so really to try to summarize, I thought I'd touch back on those three benchmarks of functionality we set in the beginning. And when we take a look at that first one, we see that although timing of vegetative development varied between the two landscapes, both landscapes evolved into diverse plant communities comprised of largely native species in the region. In terms of carbon accumulation, we see that all plant communities within the landscape are able to sequester carbon at rates comparable to nearby sites. And as of 2019, the fen was a carbon sink and upland was on trajectory to becoming one. But I really think that the biggest takeaway here is the ability for the system to continue performing under both periods of water stress and salt stress. Moreover, it really solidifies that reclamation in the region is possible in terms of plant functionality, even when using the byproducts of bitumen extraction as substrates. And so results from this study provide some context for plant community performance in these novel reclaimed settings, and may aid future design in terms of planting prescriptions and design overall. So thank you guys very much. And I think I might be over time for any kind of questions. Thank you.
Thanks so much, Nataša, for the great talk. It's great to see all that huge data set come together in such a great and coherent way. I think we are just right on time here. So I would suggest if you have questions, there could be time for one question. As well, if you put it in the Q&A, Nataša can respond over the text function there, or my last suggestion would be to follow her on Twitter for great science content. And it looks like we have a raised hand, so maybe if we do it one time for a quick question.
Sorry, can I go ahead?
Yep.
Thank you very much, Nataša. That was awesome. Thank you. I have a very quick question in terms of soil properties. Did you notice any change in the actual properties of the soil? And I'm thinking here, just spitballing, active porosity or any changes that might have happened as a result of that initial project, as, I don't know, soil compaction and all that. So did you see any sort of reclamation in that respect? Thank you.
Yeah, so especially in the peat itself, because it's donor salvage peat, and so that's basically peat that was, stripped off at the beginning of when they cleared an area, and then it kind of sat there. So that peat also kind of dried out a little bit, and then because it was moved around with that heavy machinery, and then also laid down with heavy machinery, we do see a lot of compaction in that peat and changes to both bulk density and porosity, which does have implications for the water storage properties of peat itself. Not my area of specialization. There is some really great work that's been done on those peat properties at both of the reclaimed sites. In the region, though.
Okay, thank you.
Excellent. Thanks so much, Nataša. And I believe next I will pass this over to Miranda to introduce the remainder of our speakers for today.
Yeah, thanks, Matt. Hey, everyone. My name is Miranda Hunter, and I'm going to be introducing these next three speakers. And I'm joining in today from my fieldwork site in central Alberta, which is on Treaty 6 territory and Métis Nation of Alberta, Region 4. So yeah, our third speaker today is Megan Schmidt from the University of Waterloo, and she will be presenting her work on the impacts of peatland seismic line restoration on carbon dioxide and methane. So you can go ahead and share your screen, Meg.
All the buttons. Hi, my name is Megan Schmidt. My pronouns are she, her, and I am a second-year master's student at the University of Waterloo in Waterloo, Ontario. I'm going to be presenting the results of one of the chapters of my master's thesis, which is on the impact of peatland seismic line restoration on carbon dioxide and methane fluxes. Sorry, I just need to close this. So first, I'd like to acknowledge that I live and work on the unceded traditional territories of the Attawandaron, Anishinaabe, and Haudenosaunee peoples, and that my study took place on the unceded traditional territories of the peoples of the Treaty 6 region and Métis Nation of Alberta, Region 4. I'd like to thank my supervisors, Dr. Maria Strack and Dr. Scott Davidson, our collaborators at the NATE Boreal Research Institute and Mount Royal University, my field partners, Taylor Vidopia and Miranda Hunter, as well as all the other grad and co-op students that helped me in the field and the lab over the last couple of years, and the Government of Canada for funding through the Environmental Damages Fund. So I've had a pretty good introduction to peatlands already with the previous two presentations. So just a quick one here. Peatlands are unique wetland systems where production and growth of vegetation outweighs decomposition, which leads to a buildup of organic material that can be several meters deep. 3% of the Earth's land area is covered by peatlands, and this stores about 30% of the total global carbon pool. All provinces and territories in Canada have peatlands, and it amounts to approximately 30% of Canada's total land mass. In Alberta, specifically where my project site is, there's about 134,000 kilometers squared of peatlands. So seismic lines specifically is what I focused on. And peatlands are adapted to a lot of natural disturbances like fire and flooding, but not adapted to anthropogenic disturbances such as forestry, roads, oil and gas exploration, and these lead to long-lasting damages in the peatlands. So seismic lines in particular are used for exploring and mapping underground deposits of oil and gas, and they leave these long, linear, narrow lines throughout the boreal, and they crisscross across the landscape. In preparation for seismic line use, they clear all the vegetation and trees, as well as flatten the topography so that the equipment can come through. And because they were so narrow, it was thought before that they would recover naturally, but up to 60 years later, most of these lines are still on the landscape. So we're now realizing that they are probably going to need some help. So in total right now in Alberta, there's over 345,000 kilometers of seismic lines through peatlands, and that's enough to go around the world more than 3 times, just to put that in a little bit of perspective. So when they're undisturbed, peatlands, take up CO2 through photosynthesis and vegetation, and then they re-release a bit of carbon through respiration and decomposition. So under aerobic conditions, this carbon is released as carbon dioxide, and under saturated conditions as methane. So the removal of vegetation as well as compaction and wetter conditions created on the seismic lines is thought to decrease the CO2 uptake and increase CO2 and methane release. But there hasn't been much research done on this, but we think that this could turn these lines from a sink into a source, and given the amount of them on the landscape, potentially be contributing quite a lot to greenhouse warming. The restoration of seismic lines has been a fairly recent topic, and most of the interest has been coming from forestry as well as conservation, because a lot of these landscapes are also caribou habitat. So the lack of the trees on the lines creates these open sight lines and gives access to the caribou habitat by predators like wolves. And restoration has focused then on blocking those sight lines and creating obstacles for wolves and other predators to move along those lines and get to the caribou. And that's mostly been done by creating these artificial mounds and then planting seedlings on top. So although there's been a fair bit of work done on vegetation along these lines and with the restoration, nothing has really looked at greenhouse gas exchange so far. It's just starting to get into the last couple of years, getting a couple of papers published on that. And typically, as you can see from these photos, and because they are made to block these sight lines and create obstacles, the mounds are quite large. As well, they're often inverted so that the deep peat or even mineral soil is exposed on the top of the mounds to plant the trees into, and it leaves behind quite large pools in the hollows. So my objectives for this project were to determine the environmental relationships on the lines and if and what influence they have on carbon dioxide and methane fluxes, and then to compare the carbon dioxide and methane fluxes between our treatments. So we have two mounding techniques that we use to recreate the microtopography on the lines. And we aimed with these to create smaller hollows and mounds and ensure that they're not inverted so that the vegetation stays on top, and keep them to a fairly low density so that we're not disturbing the entire length of the line again, and also to provide some structure for the new hummocks and hollows to be formed on top of. So our restoration work was done in March of 2019 when the ground was still partially frozen, as in an attempt to reduce any further disturbance just from our equipment. And the two types of mounding that we did are inline mounding, and this is where we took a scoop of peat from on the line itself and then placed it vegetated side up next to the hollow it created. And then hummock transfer, where we actually targeted naturally formed hummocks that were slightly off the line and then moved those on and placed them onto the line. So the hollows in that instance are actually slightly off the line in the natural within a few meters. And then we're comparing that to natural fen surrounding it, as well as untreated sections of the line that act as our controls. And our fen site is split into two subsites. One half is rich fen and the other is poor fen. And the treatments and collar sets were all duplicated in both sides just to capture that variation. And the collars were paired between the hummocks, the created hummocks, and the associated created hollows. And then we targeted as best we could in the natural and in the untreated section to try and target those hummocks and hollows, or highs and lows, as it were, on the untreated sections. I measured fluxes with the closed chamber method, and then measured concentrations with Lycor for methane and an infrared gas monitor for CO2. And these just both allow the concentration to build or decrease in the chamber and then be read. So just an overview again of how we measure CO2 production. So gross ecosystem productivity is the uptake of carbon dioxide by plants via photosynthesis, and then ecosystem respiration. And here I do not differentiate. We combine autotrophic and heterotrophic respiration, as Tracy was talking about. So we just call it ecosystem respiration as a whole. And that's the output from the roots, microbial communities in the soil, and that's put back into the atmosphere. And then the difference between those two is the net ecosystem exchange, which tells us the magnitude and the direction overall of carbon movement. So getting into my results from 2019 and 2020. First, we'll take a look at the GEP, which again was the uptake. So we did find too that we did check, and the fen type wasn't significant between the treatments or collars. So since we're mainly interested in the treatment impacts anyways, we left that out and just use it to capture the variation. And the results of an LME model found no significant differences between natural and untreated in either year, even though untreated was actually slightly more productive. And the average productivity significantly was reduced in, which means less carbon was taken up in both of the treatments, which is unsurprising given that we caused disturbance during our restoration. But in the second year, the hummock transfer technique was already starting to improve slightly. And over the whole 2-year data set, in general, shallower water table decreased carbon dioxide uptake, particularly in the inline mounding section, and an increased soil temperature increased carbon dioxide uptake except in natural sections. And productivity overall increased with increased moss and vascular cover. And you can just see I have the means here in the top from 2020, and there's actually quite a variety between, quite a range between the treatments. So then ecosystem respiration. Again, there was no significant difference between any of the treatments or any of the microforms in 2019. Then by 2020, there's actually quite a range of respiration between the microforms, but again, still no significant differences between the treatments. Excuse me. So in inline mounding, the hummocks released the most CO2 out of all of the treatments and microforms, followed by hummock transfer. And then the hummock transfer and inline mounding hollows, actually had the least ER. So this is possibly due to the exposure of the previously buried peat in the two hummock types, and that creates oxidated conditions instead of saturated. And then in the hollows, we essentially moved all of the vegetation and roots, and they were saturated to surface level or flooded for the whole time, which leans more towards the production of methane than respiration of CO2. And again, for ecosystem respiration, deeper water table, so drier conditions at the soil surface, warmer soil temperatures, and increasing vegetation cover all contributed to increasing respiration rates. And then finally, ecosystem exchange, which is just looking at the differences, or looking at the overall difference between uptake and production. So overall, inline mounding and hummock transfer were both much lower in NEE, although they did improve from 2019 to 2020. And soil temperature, water table, vegetation, none of them were found to have any significant effects on NEE. But considering that NEE is looking at the difference between uptake and release, it measures a lot of the same things, and a lot of that can cancel each other out. So it's not that surprising that we didn't see huge effects of the environmental conditions. And then for the total NEE as well, we wanted to look at the treatments as a whole, because obviously with the collars, we're only targeting those specific microforms, but we were not sure what the effect was across the whole treatment, if it was helping or hindering the places in between that weren't a hummock or a hollow. So to do this, we were able to figure out the proportion of the hummocks and hollows and the area and densities on the line. And we used the values from the untreated control section to apply to the flat undisturbed section between the hummocks and hollows in the two treatments. And with those, we were able to then figure out this estimated total NEE for the treatment. And this isn't a full growing season estimate because measurements were only done in July and August, and this is only for the understory, so it doesn't take into account any of the trees or shrubs that would be taking up and potentially releasing carbon in the natural area. And finally, our CH4 results. So there was overall saturated conditions creates higher CH4 release in hollows anyway. This is also influenced by vegetation and soil temperatures. So barring the high production in inline mounding hollows and the low production in natural hummocks in 2020, there were no significant differences between microforms or treatments for CH4 production. The lower CH4 in natural hummocks and in hummocks in general is likely due to the thicker anaerobic layer. So this allows methane that's being produced lower in the peat as it diffuses up through the oxygenated peat layers before it reaches the surface, it can actually be reduced to CO2 by the microbial community in the soil, and then that way it reduces methane. And this also correlates to the low ER in the mounding treatment hollows, which were consistently saturated, so they don't have that anaerobic or that aerobic layer to transform the methane. And one thing that was really neat with using the LICOR that measured every second was we were actually able to capture ebullition events or methane bubble events and parse out how often they happened and how much, like what the concentration was of those bubbles. So you can see we captured no bubbles in the natural section at all. We had a couple on the untreated lines, a few more in the hummock transfer, and inline mounding was by far the most ebullition and also the highest concentration. And these numbers are all added onto those diffuse fluxes that we were measuring with our 3-minute fluxes. So just in summary, untreated seismic lines were found to not be significantly different from natural, even though there were shifts in temperature, water levels, and vegetation covers. Restoration treatments did significantly decrease CO2 in the first and second year post-reclamation versus the natural and untreated, and also increased methane production. Of these, inline mounding had the lowest uptake and the highest methane emission, and restoration treatments, specifically the inline mounding, increased methane ebullition events. So treatment, microform, and water table we found were the most important factors in both carbon dioxide and methane fluxes. And we're not sure at this point if any E from the hollows and the rest of the line could actually increase enough to compensate for those high methane fluxes, and especially that high methane ebullition. So at the moment, we're not sure what type of restoration is the best. It is good to note that this didn't include any trees, so that would shift and improve the NEE of the natural section, but we're not sure by how much. And we need to just continue to measure our site in the future to see what the long-term effects are on carbon emissions. And also it needs to be applied and measured in other diverse systems to see if one of the restoration methods is effective, if it's effective equally across all of the different peatland types. Thank you.
Thanks, Megan. That was really great. Yes, we should have time for a question or so. So, oh, it looks like we have someone who has raised their hand. And yeah, I think you've been given permission to speak, so you can go ahead.
Thank you. Thank you very much. That was a great presentation. I have a quick question with regards to the seismic lines. And I'm not sure if it's a little bit outside of your scope, but I was just curious, is there any natural overall recovery of the seismic lines in the area that you worked at? The reason I'm asking this is that I did some work on seismic lines in Northwest Territories, different sort of situation, but they were not recovering naturally. And I was wondering if you could comment on that, if you have seen any sort of succession of plans towards that recovery. Thank you.
On our site, there was no recovery. We have a few very baby trees and a handful of shrubs that have come back onto the line. But for essentially there's been no recovery. And our lines in particular are at least 30 years old, more than 30 years old. So they've been there for a while. There's been some studies on other seismic lines and also some oil sands exploration well pads, which are generally connected and part of the whole system of linear disturbance. And some places they have found some tree recovery and also some bryophyte recovery, but it seems to really depend on the site. Depends on how much kind of compression happened and if, yeah, just like what's been able to kind of move in. There is a little bit of microtopography starting to develop on our untreated lines, but the difference is like a few centimeters between highs and lows. So it's not the typical kind of hummock hollow profile that we're used to yet. So yes, general consensus, especially since a lot of these lines are called legacy lines and they've been on the landscape for around 60 years or more, doesn't seem to be much recovery.
Yes, thank you very much, much appreciated. And just in case I missed that, there isn't any permafrost there, is there?
No, we're out of permafrost.
Okay, thank you very much, Megan.
Okay, and we're going to do one more quick question. So this question is from Nora, who said, "Great talk. Sorry, I missed this. How did the magnitude of diffusive versus ebullitive fluxes compare?" I think specifically for our methane.
I'm just going to pull the numbers up so I actually give you the right ones. It was like magnitudes higher. So in the untreated lines, it was approximately 100 milligrams of methane per meter squared per day higher, and about the same in the hummock transfer. And then for the inline mounding, and most of this was coming from the hollows in inline mounding, which are the ones that were on the line. So they are quite, they're the deepest ones as well and wettest. The mean diffusive flux was 775 milligrams of methane per meter squared per day. And the ebullition, the ebullitive flux was 1,775. So an order of magnitude greater. And that captured about, we had ebullition in about 5% of those fluxes. So works out to a fair bit of methane.
Great, thanks. Okay, so I think we'll go on to our next speaker, who is Hongxing He from the McGill University, and his talk is titled "Water Level Variation at Beaver Pond Significantly Impact Carbon Uptake of a Continental Bog." So you can go ahead.
Yes. Okay, it's a bit slow. I guess it's coming. Hello, everyone. I hope everything works fine, both the slides and my sound.
Yeah, it looks good.
Yes, great. Thanks, Miranda. So my name is Hongxing He. I'm a postdoc at the Department of Geography at McGill University. So today I'm going to present an ongoing study that me and my co-worker are currently working on. The title of my talk is "Water Level Variation at the Beaver Pond Significantly Impact Carbon Uptake of a Continental Bog." You can see my co-workers here listed. So a little bit about the study background. As you have already heard a few times, global peatlands is important in terms of global carbon balance. The figure at the right shows how the peatland profile, that's the growth of the vascular plant and the sphagnum mosses through photosynthesis, uptake carbon from the atmosphere, and the respiration returns part of the carbon back, and because of the high water table at the peatland, so the anoxic conditions reduce the decomposition. In this way, the carbon accumulates in peatland. So globally, peatlands cover 3% of the land, but contains 30% of the global soil carbon. In terms of Canada, peatlands cover over 1.1 million square kilometers, which is equivalent to roughly 12% of the Canada's total land area. And this huge carbon stock in Canada are threatened by ongoing climate change and human management. The carbon dynamics of peatlands are particularly sensitive to the change of hydrology, as the hydrology both regulate the photosynthesis and the respiration. In North America, beavers are common in the lakes. The lakes defined as the margin of the peatland, as you can see in the figure below. So the beavers living in the lakes, they built beaver dams, they changed the water level at the beaver pond, and by this they changed the hydraulic gradient, thus modify the natural subsurface flow. In this way, they can have potential impact on the carbon uptake of the bog or the peatland. So the overall objective of our study is to quantify and evaluate the impact of water table variation in a beaver pond in the lake adjacent to a middle continental bog and carbon ecosystem carbon dynamics. To do that, we applied an ecosystem model, a COOP model, to a continental bog system, Mer-Blue in this case. The COOP model has been applied for a number of peatlands in Europe. I have listed those peatlands here, and most of these peatlands are fenced, except one restored bog in UK. That's why in this study we also aims to evaluate the model for this continental bog system that has never been applied before. So a few words about the study site. So, as already mentioned, it's a Mer-Blue bog. It is a large nutrient poor bog located at Ottawa. And in the right, it is a figure, a bird view of the study site, Mer-Blue. The vegetation cover is a typical bog vegetation. It has sphagnum mosses and evergreen shrubs. And the average peat depth is around 4 meters. Mer-Blue was continuous monitoring using eddy covariance technique from 1998 until today. So we have more than 20 years of continuous data from this site. And we have at Mer-Blue, we have various disturbance of the beaver dams. As you can see from the figure in the right, the lake close to the peatland, and the beavers they're living in those beaver ponds in the lakes. And in the next slide, I will tell you what do I mean by disturbance of the beaver dams. In this slide, you can see two measured water levels. The upper one, the black thick line, is the measured water level at the peatland. As you can see, they are generally stable, but with some drop during the summer period. The next line shows the measured water level at the beaver pond, which is more variable over the last 20 years. This is because of the human disturbance. From 1998 to 2004, the first 60 years or so, there's continuous beaver trapping and dam breaking in the beaver ponds. This reduced the water level at the beaver ponds around 1 meters. And again, another disturbance occurred during the autumn season of 2012. At that time, beaver baffler was installed and the dam was breaked. By that time, the intention was to do an uncontrolled experiment. This disturbance lowered the water level at the beaver pond by 30 centimeters. And the third disturbance for the beaver pond was in May 2018, where the beaver dams was partially open. So because of this various disturbance, we group them according to the lowered water level at the beaver pond. So for the first 6 years, we call it high disturbance level over this period. And from 2012 to 2016, we call it a medium disturbance level, and the rest of the period is low disturbance. So this sets a great variation to study the disturbance of the water level at the beaver pond to the hydrology and the link to carbon dynamics. So a few words about Coop model. So the Coop model, it is a coupled mass and energy transfer model for soil, plant, and atmosphere system. The main model structure is a one-dimensional vertical layered soil profile, as you can see here. The left part shows the water flow, and the right part shows the heat flow. All of the major hydraulic process like evaporation, surface runoff, water uptake by roots, and natural transport, they are all simulated. For soil heat flow, the many conduction and the convection are simulated. What happens in this soil profile for temperature and water will impact and the decomposition and the plant growth. In this way, it impacts the carbon, nitrogen, and phosphorus flow. So the model can simulate the carbon, nitrogen, and phosphorus and dynamics. And the growth of the plants will change the ground cover. In this way, it will also change the aerodynamic resistance. In this way, it will change the surface energy balance and this energy partitioning. And the changed energy partitioning will once again impact and the soil, water, and heat simulations. So the Coop model, the key message is it is a strong physics-based model. It has a strong coupling between the biotic and abiotic process. It is also open software that can be downloaded freely from the website that I put it here. So I'm going to show some simulation results at the measured data. Now, from this slide shows the 20 years hydrological fluxes. So the top figure shows the measured annual accumulated precipitation, evapotranspiration, which is the blue color, and the total runoff, the dots that measured at the outlet of the catchment. Again, this as a measured accumulation values for each year. And the second figure shows the model simulations of the corresponding hydraulic fluxes. And the third figure shows the measured and the simulated water table depths, where the rate cross is measured and the blue line is simulated. So as you can see, in terms of the annual average numbers, the evapotranspiration simulated value was 430 millimeter per year, which is close to the measured by the AD tower, which is 490 millimeter per year. The models simulates the subsurface flow, which is the lateral flow from the peatland to the beaver pond, with an average value of 327 millimeter per year. And the surface runoff, this many occurs during the slow melting season. The simulated was 220 millimeter per year. The total runoff, which is the sum of the subsurface flow and the surface runoff, the simulated value was somewhere around 550 millimeter per year, which is comparable to the measured at the outlet, that is 462 millimeters per year. So the key message from this is the model simulates the hydrology very well for the 20 years of Merblue data. So how about the carbon fluxes? This slide shows the comparison of the measured GPP, the first figure A, ER, which is ecosystem respiration, figure B, and NEE, later ecosystem change, and figure C. Again, the red is a measured and the blue is simulated. And the figure below shows the scatter plot, shows this with the simulated and the measured data. So as you can see, the model again did a very nice job to reproduce the measured 20-year carbon fluxes. There seems some discrepancy in the NE simulation during the spring period. The blue line, which is simulated, is higher than the measured data slightly, which means the model seems have a higher uptake compared to the measured data. But except that the model did a very nice job for simulating the carbon fluxes. So this figure, the top figure shows the mean accurate cycles over the growing season. So which is the cycles of the oxic layer during the growing season. The figure below shows the annual average NE uptake. So I have grouped this more than 20 years data into the disturbance level based on the disturbance to the beaver pond. So as you can see, when we have a high disturbance to the beaver pond, which means the water level at the beaver pond is lower, that means a dry pond. Then the oxic layer in the peatland is higher, and the annual NE uptake is lower. So which means the higher disturbance to the beaver pond will reduce the uptake of the peatland. And here shows the sensitivity of the water level at the beaver pond. That is the x-axis from the left to the right, which means from a dry beaver pond to a wetter beaver pond, and the corresponding simulated NEE, GPP, and ER fluxes. As you can see, from the right to the left, which when the water level at the beaver pond decrease, which means a higher hydraulic gradient to the beaver pond, this will decrease the carbon uptake of the peatland. And after a certain threshold, which is somewhere around 68.2 meters, the peatlands will switch from a sink to a source even. And the reason of this is because the increasing GPP, which is shown as a square line, cannot catch up with the sharp increase of the ER, ecosystem respiration, which is shown as a triangle here. So to summarize, our model exercise overall shows Coop model can simulate the carbon dynamics and its associated drivers of a continental bog system. And we also found that management of the beavers and the beaver dams from the first 6 years lowered the pond water by somewhere around 1 meters than today. And this lowered the carbon uptake by 55 gram carbon per square meter per year. To put this into perspective, this is half of the current peatland carbon uptake, which is somewhere around 110 gram carbon per square meter per year. The carbon uptake of Mer Blue Bog shows a linear relationship with the water level at the beaver pond, and the slope is somewhere around 120 gram carbon per square meter per year per meter. This means this 1 meter decrease of water level at the beaver pond will reduce 120 gram carbon per square meter per year at the bog. Finally, our modeling exercise also predicts a tipping point of 1.7 meter below the peat surface for the bog system to be function as a carbon uptake system. Within that range, the bog will be a carbon uptake, but across the tipping point, then it will switch from a sink to a source. So that's all from me. Thanks for your attention, and I would love to answer any of your questions.
Thanks. Yeah, so I think we should have time for a quick question. So if anyone, either you can type it in the chat or you can raise your hand and then we'll let you ask it. Okay, it doesn't look like we have any questions coming in, but you can always email any of the presenters afterwards, and I'm sure they'd be happy to chat about their research. So thanks, Hongxing, and we'll move on to our final speaker, who is Karl Friesen-Hughes. Sorry if I'm not pronouncing your last name right, from the University of Winnipeg. And the title of their talk is Source and Fate of Dissolved Organic Matter in a Boreal Headwater Catchment Under a Changing Climate. So you can go ahead and share your screen.
All right, so I should be good to go. Okay. All right, yeah. Well, hi everyone. My name is Karl. I'm a grad student in my first year of my master's at U Winnipeg, working with Dr. Nora Casson. So I've been living the all virtual life so far. But I'm going to be talking today about the source and fate of dissolved organic matter in a boreal headwater catchment under a changing climate. But I should note that I have not yet completed my fieldwork or started my analysis. So this is a bit of an early look at my work. So my work is obviously focused in the boreal forest, which is the largest land biome on Earth. And there's also a high degree of landscape variability here. So there's all kinds of forests, wetlands, streams, and lakes. And the boreal forest is experiencing the most significant temperature increase of all forest biomes in the 21st century. Precipitation patterns and snow dynamics are also expected to change as climate warming continues. And we also expect to see more frequent and intense extreme weather events such as storms and droughts. And climate change is bound to influence how carbon moves and transforms as it goes across the boreal region. And the boreal forest is a significant part of the global carbon cycle. So if we can understand how carbon is cycling through terrestrial and aquatic ecosystems, it's going to help us predict future conditions. And the controls on carbon storage and transport between ecosystem components like forests and wetlands are not so well understood. So this limits our ability to make more accurate models. My research question is, how does the terrestrial source of dissolved organic matter, or DOM, influence the quantity and quality of DOM downstream in a boreal headwater catchment? So essentially, how does the origin of DOM affect its downstream fate? And I'm going to answer this with two related hypotheses. The first of which is that the quantity and quality of soil pore water DOM will correlate with proximal soil properties. Second is that the relationship between the quantity and quality of soil pore water DOM and downstream DOM quantity and quality will depend on discharge. So it's sort of this continuum where we're looking at the soil, how it's going to the soil pore water, and then how it's going to the stream water. This research is going to take place at the International Institute for Sustainable Development's Experimental Lakes area, and acquiring intensive field measurements within the context of the long-term data that is present here is going to help us disentangle those controls on DOM source, transport, and transformation, and how these are shifting under a changing climate. The big picture here is showing a map of the Lake 239 catchment, which is where my study takes place. you'll notice that there are 3 sub-basins. There's the east, the northeast, and the northwest. And being able to compare these 3 is going to be really helpful for also contextualizing our results within that landscape variability that I mentioned earlier, because they differ in a couple of key ways, like size, stream extent, and peatland coverage. This map here is a digital elevation map of the catchment around Lake 239. The blue triangles indicate the presence of a weir, which is the picture at the bottom right there. This is where we will collect weekly stream samples from, and this is also where flow and water chemistry has been measured for the past 50 years. The red dots indicate the presence of lysimeters, which we've already installed, which you can see at the top right. And these are what we'll use to collect soil pore water samples. We also plan to collect soil samples really close by to each of the lysimeters, so hopefully within a meter or so. And the buffer zones around each group indicate the sort of proposed areas that we plan to collect those distal soil samples. So we'll get them from a range of directions and distances from the lysimeters. And then some of the techniques for the soil. As you might expect, some of these more classic soil properties like bulk density, soil moisture, texture, and soil organic matter, but also these other metrics like particulate organic carbon content and something called permanganate oxidizable carbon content, which is used to measure the labile carbon and is also related to microbial biomass and particulate organic carbon as well. But the other key thing is that we're planning to extract soil leachate, which means that we're going to be able to do the same set of water analysis on the soil leachate, the soil pore water, and the stream water samples. For water sample techniques, there's going to be some classic like quantity techniques, so looking at different dissolved nutrient concentrations like carbon and nitrogen and the ratios between them, and then also different water quality metrics like within absorbance, things like specific UV absorbance or SUVA, and then also fluorescence, so things like excitation emission matrices and all of those related indices. And a lot of those quality metrics are really useful in trying to figure out the origin of the DOM. And then also, obviously, we've got that stream data, so we are going to do some hydrological techniques, so things like concentration discharge relationships and antecedent moisture conditions as well. And then finally, just some brief next steps. I'm actually heading out back to the field on July 19th, going to be going and collecting water samples from those lysimeters, also trying to do all of those soil samples. So that's going to be a lot of bushwhacking. And then going to be beginning that soil and water analysis once we get back at the end of July. So for now, this is just a to be continued. So hopefully next year in Saskatoon, I've got much more to get into detail about. And then just finally, some acknowledgements. Of course, thank you to Dr. Nora Casson and our wonderful lab group for supporting me so much through this last year, and especially to Dr. Matt Morrison, who's also on the call, who has greatly helped with all of the fieldwork that I've done so far. Also to my funding, which I have received from the University of Winnipeg and from NSERC, which makes my research possible. And then finally, thanks for having me. Thanks for sticking around till the end. And it was, so great to be able to attend CGU this year and hear all these talks. And really looking forward to attending in person in the future. So that's it for me.
Thanks, Karl. So if anyone has any questions for Karl, they can again either put it in the chat or raise their hand. Okay, I will just go over some end wrap up stuff. And if anyone does post a question as I'm talking, we can go on to that. But I want to thank all of the speakers and all of the attendees for coming today. this wraps up the final Biogeosciences session of this summer series. There are 2 more sessions coming up that I want to draw your attention to. On Thursday, July 15th, there is a session on lithospheric tectonics and mantle dynamics. And then on Tuesday, July 21st, there's a session on hydrology and geophysics in high latitude and high altitude environments. And I think before we end, we're going to play a short promotional video for next year's in-person CGU event. Great. Well, that wraps up this session. So yeah, thanks everybody for coming and hope you have a good rest of your week.